ZMA 261 Fall 2022 Final Exam. Question 1. Find an equation of the tangent plane to the paraboloid z equals 1 minus 1/10 x squared plus 4y squared at the point 1, 1, 1/2. All right. I guess if it really helps, I don't think it will. This is kind of the shape that we're looking for. Hopefully you know that from the minus sign, and given that it's a paraboloid, but doesn't really matter if you can't visualize it. I think it's just helpful to know anyways. Okay. Tangent plane. So we know our standard equation or standard form of tangent plane we can write as um, we're going to get the x partial of f um, times x minus a uh, plus the y partial of f times y minus b plus the z partial of f times z minus c equals 0, where our point is a, b, c. That's the point at which we're looking for the tangent plane. And fx, fy, and fz are the partials of some function f of x, y, z. And we can find that f of x, y, z by just adding this 1 over 10 times x squared part to the left-hand side. So we're going to get 1 equals, or I guess I'll keep the formatting. So 1 over 10 x squared. I'm multiplying these out plus 2 over 5 y squared plus z equals 1. Okay. So I just added and multiplied out the 1 over 10. Okay, so now let's find our fx, fy, and fz. Fx is going to be equal to 1 over 5x. Fy is going to be 4 over 5y. And fz is just going to be a nice 1. Okay, now we need to plug in our point to each of these three functions, and then we can use our form up here. Okay, so we're going to get 1 over 5 times 1, or just 1 over 5 times x minus 1 plus 4 over 5 times 1, same thing, times a y minus 1. And then plus, we just have a 1, so we can just ignore that, z minus 1/2. And this is all equal to 0. Pretty cool stuff. Okay. Now it's just grouping here, or I guess combining like terms. We're going to get 1 over 5x minus 1 over 5 plus 4 over 5y minus 4/5 plus z minus 1/2 equals 0. And we didn't really need to do all that work, but we're just looking for really, let's see, we're looking for the constant term, because I notice 1/5, 4/5, and 1 only happen in answer E and C, or no, sorry, E and B. So A, D, and C are all gone because of the coefficients out in front. So constant term, what is it going to be? It's going to be negative 1/5. Well, actually, they're adding it to the right side. So let's just rearrange here. Plus 4 over 5y plus z. And then let's see, 1 over 5, or negative 1 over 5 minus 4/5 is just 1, minus 1/2 is going to be minus 3/2 equal to 0. Or we can just rearrange and get equal to 3/2. And that is answer B. Question 2, find the points where f has a local extremum. Extremum, I don't really know. Whatever. For f given by f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. Okay, so we're looking for those mins and maxes. So we're going to have to use a second derivative test. And first, let's find our gradient of f and set each of those components equal to 0 to find the critical points. So the gradient of f is going to be negative 3x squared plus 4y and 4x minus 4y. Okay. So remember, set these both equal to 0 to find those critical points. And this one right here is a little bit nicer because we really just have 4x equals 4y. So x equals y. And we can use x equals y into that equation. Whoa, I don't even know what that is. into this equation and actually find the points. So doesn't matter which we replace, but let's just replace y. I like working with the x's. So we're going to get 3x squared plus 4x equals 0. And we can factor out an x to get x times 3x plus 4 equals 0. So by, I don't really know, algebra, x equals 0 or x equals 4/3. Okay, and we know x equals y, so we essentially found our two critical points. They're going to be 0, 0, and 4/3, 4/3. So that's nice. Okay, but we need to check if they're actually mins or maxes or if they're um, saddle points by using the D or the curvature, I think it's officially called, and that's going to be fxx, fyy minus fxy quantity squared. So we can get fxx pretty easily and fyy. We just remember that these are fx and fy respectively. So our fxx is going to be negative 6x. Fyy, this actually looks, my handwriting is pretty bad, but there we go. That's actually really nice. I like that a lot. Fyy is going to be just negative 4. And then fxy is equal to fyx. The order doesn't matter. Remember that. Um, it's going to be equal to just a nice 4. Okay, so let's do this out. So d is going to be equal to 24x minus 16. So if we plug in our 0, 0 into this, um, d is going to be less than 0. So that means we have a saddle point. So 0, 0 can't be a min or a max. So I'm looking at our answers. A is wrong. B and C are also wrong. So it's either up to 4/3, 4/3 being a max or a min. And for that, we can look at either fxx or fyy. And in this case, they're both going to have the same sign. This case, it's negative. And negative means if you kind of imagine like in the 2D dimension, you have like y equals negative x squared. The slope is starting out positive, but it's decreasing. Um, so naturally, we're positive, we're 0, and then we're negative here. And that means we have a max. So E is going to be our answer here. 3, find the work done by the force. F equals negative 1/2 xi minus 1/2 yj plus 1/4 k on a particle as it moves along the helix. R of t equals cosine t sine tt from the point 1, 0, 0 to the point negative 1, 0, 3 pi. That was a mouthful. Okay, first thing I like doing is checking whether the force field is conservative or not, because especially when they give you like a from to point, I just think it just kind of rings, maybe it's conservative, I don't know. Do that, we need to look at, say, two pairs of components in F. So let's say the first and the second one. And if you remember, like the first component is the X component, second is the Y, third is the Z. So we want to check if like two pairs of components, check if the opposite partial of one component is equal to the other opposite partial of the other component. So I kind of think it's hard to explain, but we basically check if the y partial of this component is equal to the x partial of that component. And then you can do it for x and these two components. So check if the z partial of the x component is equal to the x partial of the z component. Um, Hopefully that makes sense. So let's do that for the first two. Well, y partial of this is going to be equal to 0, and x partial of this is going to be equal to 0 as well. So that works. Let's do the same for these two. So the z partial of this component is equal to 0, and the y partial of a constant, of course, it's 0. That's nice. And then we just have one more to check, x and y. And sorry, we already checked that one. X and z. So z partial of this is 0, and x partial of a constant is 0. So okay, everything is all equal. That means we have a conservative vector field, or force field, whatever. So we can find a potential function, um, and that's going to be equal to basically we know that uh, these three components are some potential of x, potential of y, potential of z. So what we can do is integrate each of those components, like partial integration. Um, so phi x is equal to negative 1/2 x. So if we integrate with respect to x, we're going to get phi is going to be equal to negative 1/4 x squared. Same thing with y. We're going to get phi of y equals negative 1/2 y. So phi is going to be equal to negative 1/4 y squared. And then phi of z is 1/4. So phi is going to be equal to um, 1/4z. Okay. And what we need to really do is find like all the unique components that we got from this step right here, add them all up, and that's our total phi, if that makes sense. Okay. So we're going to get our total phi is going to be equal to negative 1/4 x squared minus 1/4 y squared plus 1/4 z. Okay, that's nice. And then we have to evaluate that from our top point or our 2 point, which is negative 1, 0, 3 pi. And we have 1, 0, 0. All good here. Okay, so our y is 0 for both of them, so we can really just cross that out. Doesn't really matter. Doesn't contribute to anything. So let's plug in our top bound. We're going to get negative 104 plus 3 pi over 4 quantity all minus, um, just minus a negative 1/4 actually. So that is just equal to 3 pi over 4, and that is answer C. Question 4, let f be the conservative vector field given by f of xy equals uh, y cubed plus 1, 3xy squared plus 1. Saying to consider a semicircular path from 0, 0 to 2, 0. That is, gives us the parameterization, and it's saying evaluate f dot dr. Okay, well, I guess we can sketch out the region. Um, so we're looking to xy from 0, 0 all the way to 2, 0. No, I did that wrong. 0, 0 to 2, 0 right here. We have a conservative vector field, so really we can just find that potential function and do our top bound minus our bottom bound. So let's go ahead and do that. So we know this component right here, similar to the last problem, is going to be equal to phi of x, our potential function, um, and this is going to be equal to phi y. So we can integrate those components. So we get phi of x equals um, y cubed plus 1. So phi is going to be equal to the integral of that, or xy cubed plus x. And then phi of y is equal to 3x, oops, what is going on? Okay, y squared plus 1. Integrate that, we're going to get phi equals xy cubed plus y this time. And then we need to combine all the kind of unique components to form our total phi. So our total phi is going to be equal to xy cubed plus x plus y, which is very, very nice. Okay. And then we need to evaluate this from our top bound to our final bound minus our initial. So that is 2, 0, initial 0, 0. That looks like a 6. Okay. And I notice um, our y is all 0. So this component is all gone. This component is all gone. So we're just left with really just evaluating x from 2, 0, or from 0, 0 to 2, 0. And that is just equal to 2. And that is answer D. Question 5, consider the circle C centered at 0 with radius 0. A particle travels once around C counterclockwise. Pretty important to note counterclockwise. It is subject to the force F of xy equals y cubed, x cubed plus 3x y squared plus 1. And we need to use Green's theorem to find the work done by F. Okay. So we know work done is kind of synonymous to integral of a curve, or I guess circle in this case, C of f dot dr. And we know from Green's theorem that that is equal to some double integral of a region D. And if we kind of sketch out our region, not the worst region in this case, and usually isn't too bad, but it's just a circle of radius um, 3 here. So this right here is going to be our region D. Um, okay. Of and also, quick reminder, if we have some f equals CQ, which is kind of what we have in this case. So this is our P, this is our Q. Green's theorem is going to tell us that this integral is equal to double integral of the x partial of Q minus the y partial of P um, dA. Okay. And dA just means dx dy or whatever you want to think of there. Okay. So we can find that qx minus py, qx minus py is going to be equal to qx is going to be 3x squared plus 3y squared minus py, which is 3y squared. So that actually means this all cancels out, so we're just left with 3x squared. And I'm thinking we're going to run into a little bit of an issue, but we're looking for double integral of d of 3x squared dA. And since we're dealing with a circle, it's pretty kind of natural to want to use polar coordinates. And in polar coordinates, we know x is going to be equal to r cos t, where t is our, or I guess I could just say theta. I think theta makes more sense. R cos theta. So when we plug in here, we're going to be left with um, double integral of 3r squared cos squared theta. And don't forget the conversion from dA to polar. We're going to get r dr d theta. And it says once completely around C counterclockwise. So counterclockwise means our theta goes from 0 to 2 pi. And our r is, of course, 0 to 3 because our radius is 3. Okay. So I guess we could clean this up, get rid of the r, and just add 1 to the exponent. Okay, cool. Not the nicest integral because we have some cosines squared, but if you don't know, okay, I guess I'll work through it. So I noticed that we don't have any thetas inside the bounds. So really, we can represent this integral as a product of two integrals, one being of r and one being of theta, just because when we evaluate the r integral, it's not going to have any theta dependence on it. It's constant, so it's just going to evaluate out without theta doing anything. So we can rewrite this as 0 to 2 pi of the theta integral, which is just cosine squared theta d theta, and then times the r integral, which is 3 r cubed dr. Okay, so if you don't know the first integral, it's equal to pi. Sometimes usually I'd say they do give you that integral. It's just kind of stupid that they would make you memorize it. But um, you can use the identity 1 plus cosine, don't even know what it is now, cosine 2 theta over 2, and then integrate that, and you should get pi as well. But this is just equal to pi. Uh, Hopefully this doesn't show up, but now you know what it is. And second integral, not too bad. We can do that pretty easily. Uh, so we're going to get 3 over 4 r to the fourth from 3 to 0, which is not that bad, thankfully. So we're going to get pi times 3 times 3 to the fourth power, which is maybe not the nicest. 3 to the fourth. 3 to the fourth, you can think of 9 times 9, which is 81. Sorry, no, I am completely wrong here. What am I saying? Uh, or is it? No, it is 81. Okay. I did not sleep enough. Okay. All over 4, and that is equal to 270, no, 243 pi over 4, and that is answer C. Wow, what a problem here. Okay. Question 6, find the arc length of the curve r of t equals 12 sine t, 5 sine t, 13 cos t, from t equals pi over 4 to t equals 5 pi over 4. Okay, so we know arc length is going to be equal to integral from pi over 4 to 5 pi over 4 of the magnitude of r prime of t dt. So first, I guess, let's find that r prime t, that is going to be equal to uh, 12 cos t, 5, 5 cos t, and negative 13 sine t. Okay, magnitude of that is going to be r prime of t magnitude, nice square root, 144 cos squared t plus 25 cos squared t plus 169. Oof, sine squared t. And this is the most satisfying part. This is just equal to 13. And that's just because, if you factor out, you can do 169 sine squared plus cosine squared t and take the square root of that. You're going to end up with 13. So that's pretty nice. So to integrate it, uh, well, integral from pi over 4 to 5 pi over 4. Where did the pi go? Hello? Okay. Of 13 dt. That's such bad handwriting. I'm upset. Okay. Is just going to be equal to the top bound minus the bottom bound times 13, or just 13 pi. Reason because we don't have any t variables in here. We don't have to worry about that. So B is going to be our answer. Question 7. What value of c makes the function f of xy equals x squared minus y squared over x minus y if x is not equal to y, or cx if x equals to y continuous? Okay, these types of questions are a little bit tricky, but always look to factor things. So I notice we have x squared minus y squared on the numerator. We can factor that as x minus y, x plus y, and then, of course, that's all over x minus y. So these are going to cancel out because we know x is not equal to y. So it's not going to be a whole or anything that you, I guess, learned in pre-calc, because you can't really divide 0 by 0, if you remember, if x were equal to y, but it's not. Okay, so um, we can rewrite this as x plus y. So if you remember, for it to be continuous, this function, we need to have um, the limit, or yeah, the limit as x approaches y to be equal to the value at x equals y. Because if you remember from like Calc 1, if it's not equal, then it's a discontinuity. So we want the limit as x approaches y of our function where f is not equal to y, which is x plus y. We want that equal to cx, which is our value at x equals y. And this limit is not too bad because we can really just plug in. Well, it doesn't really matter if you do y approaches x or x approaches y, but since we have an x over here, I think it does make more sense if we say y approaches x, because then we can just plug in y equals x. So evaluate this limit, simple plug-in, we're going to get 2x equals cx. So c must equal 2 for this equation to hold true. So c is going to be our answer. Very nice. Okay, question 8. Choose the triple integral in spherical coordinates that represents the volume of the solid bounded by the cone. C equals negative square root x squared plus y squared, and the sphere x squared plus y squared plus z squared equals 16. All right, that's fun stuff. Okay, think drawing this region is going to be the best idea here. So remember our cone, standard cone would be like z squared equals, my handwriting is not it today. Okay. Z squared equals x squared plus y squared, but they took square root and took the negative of that. So if we had the square root, it would just be the top half because everything is positive, but they took the negative. So we're really looking at the negative half of this cone right here. Okay, so just labeling the axes to make it a little bit nicer. All right, and these extend kind of infinitely. Okay, and then we have our sphere, which is going to be of radius 4. Uh, so something like that. This is going to be 4 right here. Okay, um, that's cool. So looking at our integrals, I'm just looking if we can eliminate any answers that are blaringly obvious. B and C are definitely wrong because uh, rho should be squared and sine should not be squared. So that's wrong and that's wrong. Okay. All our integrals have 0 to 2 pi for theta, which is good because we want the whole region. And my drawing is really, it's not the best. It's pretty hard to draw this, but this cone right here is really kind of going all around, um, something like that. And it's facing downwards directly. Okay. Um, so our rho bounds are all the same, theta bounds are all the same. So we really have to just focus on that phi value. Okay. Well, we're looking for, I'm going to use a different color. We're looking for this stuff right here. Um, so I'm thinking about our phi values. And well, if we have, this is our phi right here. And if we had just like this right here, this would be phi equals pi. So really, since we're below that z-axis in this picture right here, we want phi to start and end at something um, greater than pi over 2, because pi over 2 would be this right here, phi, pi over 2. So everything needs to be greater than pi over 2. So d is out, and let's look at e here. Well, is phi going from pi over 4 to 3 pi over 4? Well, maybe. Or is it going from 3 pi over 4 to pi? Well, um, okay. Well, actually, A is actually going to be our answer here. And reason is because if I draw out um, some sort of, I guess, I mean, I'm not really sure how to do it, but best way, if I draw out a ZY cross section, um, we have our sphere, of course, and then we have our cone um, that goes infinitely. We want to encapsulate uh, this whole area right here. And that means we have to end at phi equals pi. Because, I mean, this thing right here, this line right here is phi equals pi. So E can't be our answer, so A has to be our answer. And I did work with the answers here. I really think these questions are made so you do work with the answers, or else, I mean, they wouldn't be multiple choice. Eh. But yeah, this is going to be our answer because, I mean, E clearly can't be right with phi ending at 3 pi over 4. Question 9, the integral 0 to 3, 0 to square root 9 minus x squared, and square root 2x squared plus 2y squared to square root 27 minus x squared minus y squared, xyz dz dy dx. When converted to cylindrical coordinates becomes what? Okay, that was a mouthful. But, all right. I guess the most obvious first thing to do is notice that we have some sort of minus x squared minus y squared. So we can rewrite the top bound as just square root 27 minus r squared, because we remember x squared plus y squared equals r squared in cylindrical coordinates. And we can do the same thing for the bottom bound and get square root 2r squared, and that's also equal to I guess, square root 2 times r. Um, so hopefully that eliminates some bounds, or answer choices, but it does not, so that's a little unfortunate. Um, okay, it's all good. And we need to actually convert uh, also the xyz inside the integral, because if you remember, in cylindrical coordinates, we keep the z, but we change x to r cos theta, and then uh, the y to r sine theta. Um, so when we multiply those out, we're going to get um, xyz goes to uh, r squared sine theta cos theta. And don't quickly jump to answer B, or I guess it's only one, because um, we need to also convert the dz dy dx. And if you remember, in polar coordinates, sorry, in cylindrical coordinates, that whole thing dz dy dx is going to be um, well, dz dy dx is going to go to uh, dz r dr d theta. So there's that extra r. Uh, So we need to multiply that out. So we're going to get r cubed in our like integral. So B cannot be correct. Yeah. So I mean, we couldn't really eliminate that many. Actually, no, we could. We can. C is also going to be incorrect because when we multiply these out, um, we're not going to get. We need to keep the z in the integral, and C misses the z. So that's no good. Um, all right. Well, now we're just after the bounds of r and theta. Um, so uh, we're looking at the y and x part of the integral, and that looks like y is going from 0 to that square root thing, so that's the top half of the circle of radius 3, and then x is going from 0 to 3. This is the xy plane. X is going from 0 to 3, so we're only interested in that region right here. And in terms of r and theta, R is, of course, going from 0 to 3, so answer E is incorrect because it's saying it's 9. And then theta is, uh, from this picture right here, it's going from 0 to 2 pi. Or sorry, not 2 pi. What am I saying? Pi over 2. And that is answer A. Question 10, f equals negative y x z cubed. S is part of the sphere, x squared plus y squared plus z squared equals 4, above z equals 1, with upward orientation, and we're asked to compute del cross f ds of that S. Okay, well, I think it always helps to draw that sketch of the region. So we have x, y, z plane. We have that sphere of radius 4, and then we have our plane z equals 1. Okay, and the region we're after is this upper half right here because problem says above that plane. Okay, that's nice. Um, Always kind of ask yourself when you see these problems, can you simplify it using some sort of theorem or identity? And in this case, when I look at this picture, I say, what if I look like down at it from the z axis and kind of look at the xy plane? Because this plane is cutting that sphere in half pretty much, or not in half, but it's cutting it. So when you look down at it, XY plane is going to look just a circle, right? Um, and that's nice because we can apply Stoke's theorem onto that circle because we know um, this integral right here is given by um, the line integral C of um, f dot dr, where C is that boundary curve of the part of the surface that we're after. So that's really nice because we can just parameterize that circle pretty easily. So let's do that. We're going to get R of t is going to be equal to, um, well, actually, first we have to find that circle. Sorry. Um, well, we can plug in our z equals 1 to that sphere just up here, and we're going to get x squared plus y squared plus 1 equals 4, or just x squared plus y squared equals 3. Okay. So we have that. Now we can parameterize the circle, which happens to be that equation right here. it's going to be square root 3 cos t, square root 3 sine t, and z is just going to be a constant 1 just due to this thing right here. Okay, great. Now we can find our r of t, or sorry, our r prime of t. R prime of t is going to be equal to negative square root 3 sine t, square root t. What am I saying? Square root 3. Jeez, okay. Square root 3 cos t and 0. Okay, nice. And then we can plug in our f to find our f of r of t. And that is going to be, we're using this r of t right here. Plug into f. We're going to get negative square root 3 sine t, square root 3 cos t, and then just 1. 1 cubed is 1. Okay, great. Now we have to dot our f and r of r prime of t, and then integrate over that curve. So our integral is going to be from, well, we want to integrate this whole circle, and circles go from 0 to 2 pi, so that's going to be our bounds. 0 to 2 pi of f of r of t dot r prime of t dt. So we can write that as square root negative 3, and make that a little bit nicer. Square root negative 3 sine t, square root 3 cos t, 1 dot r prime of t, which is negative 3 sine t, negative square root 3 cos t, and then 0. And then this is all dt. Okay, nice. And I'm seeing some nice things going on at the dot product. Integral is going to be still 0 to 2 pi. When we dot or multiply the first components, we're going to get 3 sine squared t, and then multiply the second components, we're going to get plus 3 cos squared t, and then plus 1 times 0 is 0, still dt. And this is nice because we can just use an identity. This is just equal to integral from 0 to 2 pi of 3 dt, and that's pretty nice because that is equal to 6 pi. No complex integration needed there. And that is answer B. Okay, question 11. Find the area of the triangle that has vertices at P, 1, 2, 1, Q, 2, 3, 2, and R, 0, 2, 3. Okay, this is a Calc 3 class, so naturally you might expect some sort of cross product, because if you remember, you have two vectors, just like call them like this. Take the cross product, you're going to get the area, or take this cross product and then take the magnitude of that. That's going to be the area um, formed if you make like a parallelogram of those two vectors. So it would just be this right here. So if we have, wow, my village is getting raided. Okay, great to know. We have we have U and V. Magnitude of U cross V is going to be equal to that area right here. And if we divide that in half, we can just get a triangle. So 1/2 times that is just going to be the area of the triangle formed by those two vectors. So that's cool. We can use that. So in this case, our U and V are, I guess we can redraw it, but we're going to have, we can say this is P, P goes to Q, um, and then we have some sort of R. So we can calculate these vectors. PQ will be equal to 1, 1, 1. That's cool. And then PR is going to be equal to -1, 0, 2. Okay. And then we take the cross product of these. We're going to get there R. Okay. PQ cross PR is going to be equal to that kind of weird looking determinant of I, J, and K. 1, 1, 1, -1, 0, 2. So I could think of it this way. And then that's going to be a vector. Remember, the first component is like you cross these out, and you're going to multiply out that So 1 times 2, and then minus those multiplied out. So that's just going to be 2. Same kind of thing with the second component. Cross these out. So now we're doing these. Um, so 2 times 1 is 2. And then minus, oh, -1 times 1. So that's a plus 1. So we get 3. But remember, for the j component, we have to negate it. So this is going to be a -3. And then for the k, we're going to cross these out. 1 times 0 is 0, minus a -1, or just a +1. Okay, that's nice. And then remember, we just take the magnitude of this and then divide by 2. So magnitude is going to be uh, square root 4 plus 9 plus 1, and that's just square root 14. And we divide that by 2. I don't think we can simplify that, and that is answer D. Question 12, find R of 1 if R double prime of t equals 12ti plus 12t squared j plus k, and R of 0 equals j, and R prime of 0 equals -k. Okay, this is one of those particle motion type questions. Really, I guess not even that comfortable with the I, j, and k, so I like to write out um, my vectors in terms of like the brackets. That just lets me see it better. So R of 0 is just j, so that means we just have we have 1 in the y direction, so we really have 0, 1, 0. And then R prime of 0 um, is going to be equal to -k, so we just have -1 in that z direction. So we have 0, 0, -1. Okay, so we have our equation for our double prime of t. If we integrate that, we should get R prime of t, and then we can use the initial condition to make sure that we handled all constants correctly. Let's do that. We integrate R prime of t um, dt, we're going to get, well, we really need to integrate the vector. Um, so it's going to be 12t, um, 12t squared, and then 1 all dt. So we just integrate each component, and that's going to be um, 60 squared, um, 4t cubed, and just t. And I'm going to actually leave some spaces here. Um, Maybe a little bit bigger than. And then 1. Okay. And reason being because we need to adjust for our initial conditions, because if we plug in 0 to the vector, we have to get 0, 0, 1 given by our initial condition. And that's not the case here. Sorry, I actually messed up. This should be a t here. Okay, it's not the case here because if we plug in 0, first component 0, that's good. Second component 0, that's also good. Third component is just 0, and that's no good because we want it to be -1. How do we fix that? We just add a -1. So I actually didn't need to add these spaces, but if I did, they would have helped. Okay, so this is our R prime of t. And again, we can integrate our R prime of t to find R of t and then apply the same initial conditions. Or not the same, but the same kind of principle. Okay, let's do that. So we're going to get R of t is going to be integral of 60 squared, 4t cubed, and t minus 1 dt. And that is going to equal, let's see. Did I do that wrong? 3t cubed. I did that wrong. 2t cubed. I'm going to leave a space again to the fourth power, and then t squared over 2 minus t. Okay. And now we have R of 0 equals 0, 1, 0. First component, we plug in t equals 0, we get 0. That's good. Second component, we plug it in. Do we get 0? No, we get 0. But we want it to be 1. So how do we fix that? We just add a 1. Okay. Third component, we plug in 0, we get 0. So that's all good. So this is our final R of t, and now we're looking for R of 1. So we just plug in 1, and we're going to get 2, 2, and 1/2 minus 1 is just -1/2. And that is answer A. 13, use the method of Lagrange multipliers to find the x components only of the points where the absolute maximum and absolute minimum occur for f of x, y equals x minus 2 squared plus y minus 4 squared on the curve x squared plus y squared equals 5. All right, so if we remember, and you definitely should know for an exam or anything, with Lagrange multipliers, we have gradient of f is going to be equal to that lambda times the gradient of g of x, y, and this right here is equal to our, sorry, not the gradient, but this is equal to g of x, y. Okay, so we can find our gradient of f and gradient of g pretty easily. Gradient of f is going to be 2 times x minus 2, and gradient of, the second component is going to be 2 times y minus 4, just like that. Okay, and same thing with g of x, y. Gradient is going to be 2x, 2y. Okay, all right. And we need to set up this equation, so we need to set up each of the components. So with the first component, we're going to get, we're looking at these, or sorry, we're looking at this right here. And I'm going to multiply out that 2. So we're going to get 2x minus 4 is going to be equal to 2 lambda x. And then we can do some simplifying here. So we can get x minus 2 is equal to lambda times x. And I'm going to make that more lambda because it's kind of confusing sometimes. Okay, we have that equation. Do the same thing for the y component. So we're going to get 2y minus 8, and I just multiplied this one out. And that's going to be equal to 2 lambda y. Okay, same thing, we can divide by 2 this time. So y minus 4 is equal to lambda times y. And if we remember, we can always use our g, or that constraint function, to solve whatever we want. And I find it's easiest just to solve for x and y and plug into that curve or that equation and then find the values of lambda. And then we can back out the values of x that way. So let's go ahead and do that. From this equation right here, let's solve for x. So we're going to get x minus lambda x is going to be equal to 2. So we have x times, not x times 1 minus lambda is equal to 2. So x equals 2 over 1 minus lambda. That's nice. And then same thing for the second equation, y minus lambda y is equal to 4. So y times 1 minus lambda is equal to 4. So we have y equals 4 over 1 minus lambda. That's nice. And actually, funnily enough, the 2 right here is the reason I messed up the first time I recorded the question. So that's annoying. That's a bummer. I wasted a lot of my time, but we'll do it. Okay, now what we can do is plug into that constraint up here, and uh, x squared is going to be 4 because 2 squared over 1 minus quantity lambda squared plus this time 4 squared, which is 16 over 1 minus lambda squared, and that's going to be equal to 5. We can combine our uh, left-hand side. We're going to get 20 over 1 minus lambda squared is going to be equal to 5. And that means we're going to get 4 equals 1 minus lambda squared. So if we square root both sides, we're going to get 2 equals, well, plus or minus 2 technically, 1 minus lambda. So we have lambda is going to be equal to 3 in the negative 2 case, and we're going to have negative 1 um, in the positive 2 case. Okay, well, let's go ahead and actually, well, it's annoying because, no, actually we're fine, because we have 2 values of lambda, and it's not asking us to determine which of those 2 lambda values correspond to a min or max. It's just saying give us the values of x, where the max and min occur. So we can just plug in both values of lambda into our x and um, get the answer. Okay, so x is going to be equal to, so lambda equals 3 first, 2 over 1 minus 3. -2. So we have -1. So D, E are all gone. A is gone. And okay, well, there's no real chance x can be 0 just based off this equation, but we'll plug it in anyways. Or x is going to be equal to, for the lambda equals -1 case, still 2 over 1 minus -1 or 2, and that is 1, so our answer is C. Question 14, reverse the order of integration and evaluate 0 to 1, x to the power of 1/3 to 1 of 1 over 1 plus y to the 4th power dy dx. Okay, it's a weird looking thing, but all right, let's go ahead and kind of do our bounds, x, y plane. So y is going from uh, x to the 1/3 power. And I honestly, like, I have an idea what that is, but it's not exactly that apparent. If we cube both sides, though, we can get y cubed equals x. And hopefully you know what y equals um, x cubed looks like. And we can kind of use that same analogy to find uh, what this thing looks like. And so this is y equals x cubed. Therefore, x equals y cubed should look something like this. That's cool. All right. And, well, Clash of Clans, okay. That's, maybe I should play. I'm just kidding. Uh, okay, so that's our bottom bound here. Top bound is going to be this, which is y equals 1. And then we're going from, well, we're really just uh, integrating this kind of region right here. And I guess this right here, this is x equals 1. Okay, so we're going to reverse. So we're going to go uh, dx dy this time. And we always keep the inner integral, so we still have this. Okay, and x this time, we're going from what? Well, x, we're starting at 0, and we're hitting this curve right here, which is y cubed as we kind of derived up top. So x is 0 to y cubed, and then y is kind of nicely drawn, but we have 0 to 1. Okay, well, time to evaluate this thing right here. And we don't have any x's in here, so that's cool. We can just do our top bound minus our bottom bound to get that integral and then multiply it by this. So really we just have integral 0 to 1 of y cubed over 1 plus y to the 4th power, and that's still all dy. Okay, that's cool. And um, this may seem kind of complex, but I'm noticing in the answer choices that there's some ln action going on, logs. So, and whenever I see like a kind of this sort of thing in the denominator, I'm thinking, oh, maybe it's just log of that. So let's go ahead and try that. I'm going to use the guess and check method. So let's just guess that the integral is, let's say, ln of 1 plus y to the 4th power. Well, if we differentiate that, we're going to get, by chain rule, 4y cubed over 1 plus y to the 4th power. And that's almost what we're looking for here. But we have that extra power of 4. So if we divide this whole thing by 4, that's our correct integral. We just have to evaluate this from 1 to 0. That looks like a 6. By 1 to 0. And that is going to be, let's see, that's going to be ln of 2 over 4 minus ln of 1 over 4. And ln of 1 over 4, ln of 1 is just 0. So our answer is going to be A. Question 15, evaluate the integral 0 to square root 2, -3 to 3, xy squared over 1 plus x squared, dy dx. Okay, well, I noticed something kind of nice here. Well, it's not exactly nice, but it's not the worst. Um, our bounds are all constants, and we can kind of rewrite what we're integrating in terms of a product of two functions, which is x over 1 plus x squared times y squared. And what this means is you can kind of separate the integral into a product of two integrals because none of the, say, the y integral when we first do the inner integral is going to get like, uh, is going to be depended on by the x integral when we do the outer integral. So I think that just makes things a lot easier. So we can rewrite this as, I'm going to get rid of this. Actually, could have used it, but um, 0 to square root 2, and that's going to be our x integral. So we're just integrating x over 1 plus x squared dx times our y integral, which is not 0, my bad, which is negative 3 to 3 of y squared dy. Okay, and kind of from the previous problem, I'm seeing some ln integral here. If we use guess and check, we guess that it's this integral is equal to ln of 1 plus x squared. When we differentiate that, we're going to get 2x over 1 plus x squared. So that's almost exactly what we have here, but we have a 2. So if we just divide by 2, that 2 is going to be gone when we differentiate this. So that's our correct integral. Evaluate this from square root 2 to 0. Okay. And don't forget, we're multiplying these two integrals. Second integral, maybe not too bad. Y cubed over 3 from 3 to negative 3. Okay. And that is going to be equal to, actually, no, let's do the first one first. So this is going to be ln of 1 plus x squared, where x is square root 2. So 1 plus 2 is 3, all over 2. And then minus, we're going to have ln 1, which you know is just 0. So we don't have to minus anything. All times second integral, or second evaluation. So we're going to get y cubed, where y is 3, which is 27, over 3 is 9, minus y cubed, where y is negative 3, which is negative 27, over 3, which is negative 9 this time. So we have a minus negative 9 or a plus 9, and that plus looks weird, but okay. So we have this right here. So this is going to be equal to 18 ln 3 over 2, or 9 ln 3. Question 16, suppose that f of uv equals e to the power of v sine u, where u equals s minus t and v equals t squared. Find df dt when st is 1, 1. Okay, well, whenever you kind of see like they give you a u and v and then u depends on something, I'm thinking chain rule. So, kind of the tree diagram is nice to draw out. So f uh, depends on u and v, u and u, no, it's completely wrong. Just given from here. And u depends on s and t, but v depends only on t. Okay, so we're looking for df dt. So if we draw out our df dt, that's going to be equal to, well, we need to account for both u and v because both u and v depend on t. Say u only had like s, just for example, we would not need to account for u because u doesn't have any change in t, if that makes sense. But in this case, we have t in both u and v, so we need to account for both. Okay, so df dt is going to be equal to df du times du dt plus, so this is like the change due to u, plus df dv times dv dt. Okay, great. And let's see, let's go ahead and kind of do some of these things out. Df du is going to be just the partial of u of that thing right here. It's going to be e to the v. No, this time it's cos u times du dt, which is just negative 1, and then plus df dv, which is just e to the v sine u times dv dt, which is 2t. Okay, and notice we kind of have t and u in here, so we should probably clean that up. Well, we know s and t are both 1, so we can pretty easily find our u. So u is going to be equal to 0, and then v is going to be equal to 1. Okay, that helps a little bit. Well, we know cosine 0 is going to be equal to 1, so this whole thing goes to 1, and then sine 0 is going to be equal to 0. So this whole thing is actually just gone. So we're left with uh, e to the, just e to the 1 power, and then times negative 1, so negative e, and then plus, actually this thing goes away too. So really we're just left with negative e, and that is answer B. That's pretty nice, actually. I like that. Okay. Question 17, let f of xy equals x squared times e to the power of x plus y. Find a unit vector in the direction of most rapid decrease for f when f or xy equals 1, 1. Okay, so we see decrease. I think that's a key word. Don't forget decrease, because I pretty much guarantee you that they're going to have some negation as a correct answer or possible answer as well. Okay, so we know direction of the most uh, rapid increase is given by the gradient of f. Um, so we can compute that. Shouldn't be too bad. We are going to have to use the product rule. So let's do that. 2x times e to the power of x plus y plus x squared e to the x plus y. And then we don't have to use the product rule for y, so that's kind of nice. It's just going to be x squared e to the x plus y. Okay, maybe I didn't need to write on a separate line. That's pretty silly by me. But okay, there we go. Fix that. Great. Finally, we're done. Okay, and it's saying unit vectors, so we need to divide by the magnitude of this. But I think it's easiest if we first plug in our point. And let's not forget that this is going to be most rapid increase. So what we need to do for our final answer is just multiply everything by -1, or just negate that vector. Okay, so gradient of f xy at, or I wrote xy when I wanted to write 1, 1, is going to be 2e squared plus uh, e squared, because 1 plus 1 is 1. Uh, and then we also have e squared. Okay, so that is just 3e squared, e squared. Great. Okay, well, magnitude of that is going to be, uh, well, we can just divide by it. No, actually, I won't do that. So magnitude of gradient of 1, 1 is going to be equal to nice square root 9e to the fourth plus e to the fourth, or just uh, square root 10e to the fourth. But we can take the square root of e to the fourth, which is e squared. So we do our gradient of f at 1, 1 divided by the magnitude. That is going to be equal to 1 over root 10 times the e squared. Are actually all going to cancel because we're dividing by this, uh, and we're just left with 3, 1. But remember, this is the most rapid increase direction, so we have to negate this. So we're left with 1 over square root 10, -3, -1 as our answer. So looking at the answers, yep, I knew it. B is going to be wrong because that is increase. That is very, very wrong. A is going to be our answer. And yeah, they did the same thing with D and E. I guess in case you just didn't divide by, yeah, you didn't divide by the magnitude. So these are actually not the answer. What am I doing here? But there we go. Question 18, find the centroid of the volume bounded by z equals 1 and z equals x squared plus y squared. Okay, well, if we Remember our quadratic surfaces. This right here, the z equals x squared plus y squared is going to be a paraboloid. So let's kind of draw it out just to see what's going on here. Um, so this is our x, y, and z. Uh, I guess this is our, I'm going to make it a little bit more exaggerated here, but this is our z equals 1, and then our paraboloid is going to look something like this. Uh, and the region that we're after is this thing right here. Okay, so I think it always helps to kind of with these types of problems because they're going to be so like computationally heavy. Like you're going to be writing a lot of integrals. Hand might get tired. I don't really like that. Just think kind of physically, physical intuition. Maybe that's more like physics, but I think it works very well for this class. Um, so centroid is the center of mass. And if we kind of think about it, the paraboloid right here that I drew is completely symmetric about that line. It's a very bold line now, but it's completely symmetric. If you look down from like the z um, axis at the xy plane, it's going to be completely circles centered at 0, 0. So it's completely symmetric. That means um, the x and y center of mass have to be 0, 0. Because I mean, think about it. If it can't be zero, anything other than 0, 0, because there's no mass like over here or something like that. There's no something skewing the center of mass to either direction. It's all equal. Um, all sides of this paraboloid are pulling on the mass equally. So our x and y center of mass have to be 0, 0. So A is incorrect, D is incorrect. All right. Now, um, I guess the Z, we're only really after the Z center of mass, and we should probably compute that. And I am going to compute that, but just using physical intuition again, E is not looking too right to me because it's very, 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 very unlikely that 0, 0, 1 is going to be the center of mass because that's really going to be this point right here. And that means um, something along this line is so heavy that it counteracts all of the blue stuff right here. And that's so unlikely, especially because, I mean, we have constant mass density here. Um, so I would really guess that the centroid or center of mass would be somewhere kind of around here. Um, so I'm really not thinking E is correct, but let's actually compute that Z component. Okay, well, first we do need to find uh, total mass of our total area volume of that blue region. So we're going to use cylindrical coordinates. I think it'll be easiest. Let's do that integral. Uh, so Z is going from, no, sorry, not 1. We're going from Z equals x squared plus y squared. We can rewrite that as r squared, and it's going to go to 1. Okay, and we're integrating r dz dr d theta. Okay, our r bound, well, we can plug in or we can set these two surfaces equal to each other. We're going to get 1 equals x squared plus y squared. It's also equal to r squared, so r has to be 0 to 1. And theta is going from 0 to 2 pi because we want to go all around. We want that whole paraboloid. Okay, that's nice. So something I see is we can take out that 2 pi of theta because nothing in the inner integrals depend on theta. And that's true for the general case. So we're going to get 2 pi times, let's actually evaluate that inner integral. We're going to get, uh, actually we can rewrite this as just dz r. I think it's just a little bit nicer. So we don't have any z in that dz integral, so we can just do the top bound minus the bottom bound, which is, I'm just going to rewrite the outer. It's going to be, sorry, this is not the outer integral. It should be 0 to 1. Top bound minus bottom bound. We keep the r from here, and we're going to get 1 minus r squared. And this is all dr. And this is a little bit maybe tedious, but it's going to be 2 pi times integral 0 to 1 of r minus r cubed dr. So that's going to be r squared over 2. Maybe I'll do something like this. 2 pi times r squared over 2 minus r to the fourth over 4 from 1 to 0. Yeah, this is a little bit tedious, but not the worst. So 0 bound is going to drop out, so we don't really care about that. We're going to get 1/2 minus 1/4, which is just 1/4. So this whole thing is just pi over 2. Okay, so that means our total volume of that blue region right here is going to be pi over 2. But now we need to find that, I think it's called the z, the moment in the z direction, which is going to be um, mz. And it's going to be the same integral, but we're going to integrate, instead of just dz, we're going to integrate z dz, because if we think about it kind of intuitively, the z component is going to be like how much it's pulling in that direction, or the z, yeah, the z value is going to be how much it's pulling in that direction. Um, so mz is going to be equal to pretty much the same exact integral from here, but we're going to multiply by z. We're going to integrate by z. Okay, so again, the theta is not going to change, so I'm just going to take it out from the beginning. 0 to 1, and then r squared to 1. Now we have z dz, dr, or r dr. No d theta. Okay, cool. So I guess now maybe it becomes a little bit more, tiny bit trickier because we actually have to integrate the z. Well, yeah. So we integrate z, we're going to get 2 pi stays, 0 to 1, uh, z squared over 2 from 1, or from r squared to 1, and this is, of course, all dr, r. Okay, and I'm actually just going to cancel out that 2 because it doesn't really matter in our case. And we're going to be left with integral 0 to 1, and we just have pi out here. And it's going to be 1 squared, or just 1 minus r to the fourth power, because we have to square it. Okay, and this is all times r dr. Okay, so this is going to be pi times integral 0 to 1, r minus r to the fifth power, of course, all dr. And we're almost done here, promise. Just resize this a little bit. Okay, this is going to be equal to I times squared over 2 minus r to the sixth over 6 from 1 to 0. We don't have to worry about the 0 again. So we really just have pi times 1/2 minus 1 over 6, which is pi. I guess I'll just write it out. Don't want to make any mistakes. Which is 1/2 minus 1 over 6 is 2/6, or 1/3. So this is equal to pi over 3. And to find the z center of mass, or centroid, we have to divide our mz, which we got pi over 3, all over m, which is pi over 2. So let's see. And that is going to be, uh, m is going to be pi over 2. So we have, let's see, pi over 2, pi over 3. And this is going to be equal to a nice 2/3. So our z center of mass, or z, is going to be 2/3, and that's c. And okay, that's a lot of work just for that answer. And if you kind of wanted to, maybe if you're in a crunch, I don't know. We said before that E is kind of unlikely because it's very unlikely that zeros, or the 1, z equals 1, is going to have that much pull on this. But if you were to kind of guess, I would say maybe some value here is likely to be the z value. And just because there's more mass like at the top, so maybe 1/3 is not likely. So maybe you're just like, oh, I don't have enough time. I'm just going to pick C, and you would be correct. So that would be a good guess. Question 19, let f equals ax, cz minus ax, cz plus by be a vector field where a, b, and c, are real numbers. Yeah, thank you, Purdue Math. Real numbers. Okay, find conditions on a, b, and c so that f is not conservative and such that curl f is parallel to k. All right, so you see kind of two similar related concepts. Um, being conservative means curl F is equal to the zero vector. Um, but we want it to be not conservative, so of course we want it not equal to the zero vector. Okay, well, we also want curl F to be parallel to K. What does that mean? That means we want curl F to be some sort of vector where the X and Y components are equal to zero. Um, we want 0, 0, and just some constant C. Maybe it doesn't, not good to use C. We just want, I don't know. We use 0, 0, 1 as an answer, but 0, 0, 2 is also an answer. So something like 0, 0, K, where K is a constant. Okay, reason being because say we have, um, say like 0, 0, 1, simplest example, it's going to be pointing in this direction right here, directly along that z-axis, if we just say z, x, and y. But as soon as we change or add like a non-zero value to x and y, we're going to get something like this. It's not going to be along. Can't, because we have some movement in x and y. So that's kind of the intuition behind the vector needing to be something looking like that, the curl vector. Um, okay. Well, that means we actually need to compute the curl, which isn't all that fun, but let's make it as easy as possible. So curl F is going to be equal to, remember that kind of looking determinant weird thing that no one really likes. So we have I, J, and K of d dx, d dy, and d dz. And then we just fill out the components of the force field. Um, CZ minus AX, and I'm running out of space here. Uh, maybe I should have made that a little bit bigger, but okay. I am going to try and make that a little bit bigger. I don't know how it's going to scale, but we'll see. Uh, oh, not too bad. Okay. Okay. There we go. Hopefully I did that right. Okay. And this is going to be that determinant looking thing. So for the first component, we kind of cross these out and we do d dy of this thing right here, which is going to be b. So I'm going to get rid of this. So b and then minus um, d dz of this thing right here, which is c. Uh, okay. And then second component, we're going to do same sort of thing. So d dx of this, which is 0, minus d dz of this, which is 0. It's actually kind of nice because we don't have to worry about anything there. And then, let's see, did I do that right? Um, yeah, okay. And then third component, same sort of thing. d dx of this, which is negative a, and then get rid of that. Negative a. Uh, minus the d dy of this, which is 0, so we just have negative a. That's nice. Okay, so this is equal to our curl of f. So we said we want our curl to look something like that. So for that to happen, we want b minus c equals 0, or just b equal to c. And we want a to be equal to, we don't want a to be 0, pretty much. Because if a were 0, then it wouldn't be even, it would just be a point. It would be just 0, 0, 0. So we want a not equal to 0, and the negative sign doesn't matter. We're not really worried about which direction. It just has to be parallel. Okay, so b equals c and a equals 0. Or a is not equal to 0, sorry. And which answer is that? Is that an answer? Yeah, it's D. Question 20, find the mass of the part of the plane z equals 8 minus 2x minus y. That lies over the square 0, 1, 0, 1, where the density function is given by f of x, y, z equals 12 minus z. Okay, well, I think the key thing of this question is that it's a surface integral. You might think maybe it's a like a integrating for volume to find mass. No, it's a surface integral because it says the part of the plane and it says lies over the square. So we draw like a small image here, small sketch. Uh, our plane, let's just say it looks something like this, and maybe that's not the best drawing, but so let's say this is our 0, 1 to 0, 1. We kind of have to imagine the region that lies directly above that on that plane. That's what we're after. So yeah, okay. Well, we know that we're basically looking for a double integral of, uh, let's say that part, we call it S of really just 12 minus z ds. Um, right. And we know if we have like an explicit form of z ds is going to be equal to the square root of 1 plus zx, or z squared x, zx squared, plus zy squared, where x and y are the partials, and this is all dA. So yeah, we can find ds. So we know dx is going to be equal, or zx is going to be equal to -2, zy is going to be -1, okay? And that means our ds is going to be equal to 1 plus zx squared, which is 4, plus zy squared, which is 1. That is just square root 6. And I'm already liking that because we're seeing some square root 6 action in the answers. So that's cool. Okay, so now we can rewrite our integral in the dA land. So let's write it like this. So we have 12 minus z dA, but remember we have to multiply by the square root 6. I'm going to keep that out because it's a constant. Okay, and dA is also equal to dx dy, so I think it'll be easier if we just write dx dy. And we really know what dx, or the x bounds and the y bounds are. They just really give us those bounds, which is 0 to 1 for both x and y. So let's write those out. That's nice. And one other quick thing is that we don't have any dz's, so we have to rewrite z in terms of x and y. So we can just use our plane equation from above to do that. So it's going to be -8 plus 2y, sorry, plus 2x plus y. And then this is all dx dy. Okay, very nice. So let's clean this up a little bit. It's just going to be equal to 4 plus 2x plus y. Okay, that's pretty nice. Not too bad here. All right, so let's go ahead and evaluate this. We're going to get square root 6, keeping the outer integral. We're going to get, first doing dx, doesn't really matter which one you do first. 4x plus x squared plus xy evaluated at 0 to 1. And still we have the dy. So that's going to be, let's see, square root 6, 0 to 1 of 4 plus 1 plus y, which is, I'll keep it out, but it doesn't really matter here. It's still a dy. Okay, so that is equal to just 5 plus y, but we can leave it for there. Okay, and then we evaluate this one. 5, integral of 5 is just 5y, and then plus y squared over 2, evaluated at 1 to 0. Very cool. So what is this? The 0 is not going to matter. So we're going to end up with square root 6 times 5 plus 1/2, or 11/2. Hopefully that's an answer. Yes, it is. That is answer E.